So when we compounded daily, n was 365, compared to annual or quarterly or monthly, we ended up with more money, right? So what if we compound continuously, like every fraction of a second? How can you divide by infinity? Or how can you raise something to the infinitieth power, right? So we can't really use this formula anymore, okay? For continuous compounding, we have a different formula, but I want to show you how to come up with that formula, okay? So take a look at this right here for me. See, you've seen this before, right? 1 plus, usually this 1 right here is where the rate was, okay? We used to have 1 plus APR divided by n, and we're raising it to n times teeth power, okay? So that's the growth factor that we were multiplying our initial investment by. But let's just focus on this n, like the frequency of compounding periods, okay? So APR, let's just get rid of it. Let's not talk about any specific APR, okay? And let's get rid of this time period. Let's just ignore that, okay? Just focusing on increasing this frequency to maximum, okay? So thinking about like, what will happen if we compound every minute or every second or continuously, okay? What will happen to that growth factor, okay? So take a look at this limit table, okay? What will happen if I plug in 10 into this position, okay? I'll just write down 1, but I'll do the rest of them on a calculator, okay? So what I'm asking you to do is do this. For the second, oh, I may do a rainbow color, look. For the second one, I'm asking you to plug in 100. What if you compound 100 times in a year? So that's going to be less than compounding daily. But you see what we're doing here? We are increasing the number of compounding period per year to 1,000 and so on, right? Dot, dot, dot. So what will happen? So take a look. I'm just going to type these into the calculator, okay? So the first one, 1 plus 1 divided by 10 raised to the 10th power. What's that going to be? I'll write that down. This number is approximately 2.59374246. Now let me do the orange number. If I change the denominator to 100, what will happen? 100 there, 100 there. This is approximately 2.704813.829. Okay? All right, what about that green one? Let me see. So I copy this, but I'm gonna change the denominator to 1,000 and the exponent to 1,000. 2 points. You see it's getting somewhere, isn't it? 2.71 something. 23932 dot dot dot. Let me do 2 more, okay? So what if I change that compounding frequency to 10,000? 10,000. And I'll write down the other one too. And the last one, what about like 100,000? You know I can go on, right? The idea is that n is approaching infinity, which means us compounding continuously every second, every fraction of a second. So let me see what will happen to our numbers, okay? So the blue one, I will copy, I will copy this and change that to 10,000 and 10,000. This will come out to be 2.718145927. All right, really the last one, the purple one. What will I get if I made 100,000? We are getting 2.718268237. Now, if you are not familiar with this number, then you're like, I don't know where we are getting it. But what if they were getting at like 3.14? You know what that is, right? If they were getting at 3.14, blah, 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 you'll be like, oh, it's approaching pi. It's actually approaching a very special number too. And that special number is actually, look, that special number is actually E. You see, the whole time, this sequence was approaching our very special natural number, E. You see, it's getting close to 2.7182, blah, blah, blah. So as you increase n, as n increases and approach positive infinity, this factor 1 plus 1 over n raised to the nth power was approaching e. Okay, so this is limit, right? The limit as n approaches infinity, 1 plus 1 over n raised to the nth power is approaching e. Okay, so that's why we are using e when we are looking at situations of continuous compounding. Okay, the natural base e as the natural base denoted as e is the value given by, I'll try to write down as many as I can. Okay, 2 point, and we don't have to memorize it. There's a button E on our calculator, but that is an irrational number that never ends, doesn't have a pattern, so it will just go on like that. Okay, the quantity P, I think we're gonna now give the equation that you can use for continuous compounding here. The quantity P growing continuously at an annual percentage rate R expressed as a decimal has future value after t years is given by PERT. Okay, so anytime you guys see continuous compounding, you are gonna write down A equals P times e raised to the RT power. So here's an example down here. Our Luis, back to Luis. Okay, so he invests $5,000 in an account that earns an interest rate of 3.25%. It's the same as page 72. They want us to find the future value of his account 5 years, but this time look at the wording. If the interest is compounded continuously. So anytime you guys see that compounded continuously, write down A equals PERT. If they say compounded monthly, weekly, annually, semi-annually, then you do these formulas, okay? That orange circle formula. For continuous compounding, we are using A equals P times e raised to the RT power. So let's find the answer for him. His $5,000 getting invested at the rate of 0.0325 for the next 5 years. All right, let's see how much money he will have. I'll just use one of these lines here. Okay, let me delete these. So 5,000 times e raised to the 0.0325 times 5. So in 5 years, he will have $5,882.24. If you compare this amount to any other amount that you got on page 72 using, compounding quarterly, monthly, or daily, this amount is bigger than, this amount that we got down here is actually bigger than any other ending balance. Okay, so that is how you can solve compounding continuously type of problems. Okay.